Have you ever stopped to think what really makes a mathematical proof a proof? I mean, before we can even argue about whether it's true or false, it has to be built on some kind of logical foundation. Well, today we're digging all the way down to the absolute bedrock of reasoning to find the hidden core of every single proof.
So, here's the game plan. We're going to start with what minimal logic even is and get our heads around its core idea, the constructive principle. Then, we'll check out the rules logicians use to play with it, see where it fits in the big family tree of logic, and discover its wild role as a kind of universal translator. And finally, we'll see why its greatest weakness is actually its greatest strength.
All right, let's dive right in. First things first, what are we even talking about here? What is this foundational system they call minimal logic? To get there, let's ask a question. Imagine you strip away all the complicated rules, all the fancy assumptions we usually make. What's the most basic, bare-bones structure you need to have something you can even call a proof?
And the answer to that question is minimal logic. Now, you'll see it's called a constructive logic. We're going to unpack that in just a minute, don't worry. For now, just think of it less as a tool for proving crazy theorems and more like a magnifying glass for looking at the very architecture of a proof. It's the simple blueprint underneath all the more complicated stuff.
And you know, this isn't some brand new idea. It actually goes back to the 1930s, to a logician named Ingabri Johan Sansson. What he did was pretty clever. He took a more established system, called intuitionistic logic, and just started carefully removing rules until only the absolute must-have essentials were left.
Okay, so I've thrown that word constructive out a couple of times now. This is probably the single most important idea to grasp about minimal logic. It's really a whole philosophy about what a proof is supposed to do.
This quote really nails it. See, constructive logic demands that a proof shows its work. It's not enough to just say something is true by proving its opposite is impossible. No way! You have to actually build it, construct the thing, give a direct example. And minimal logic? It's the purest, most stripped-down version of that idea.
So if this logic is so incredibly simple, how do logicians even analyze it? You know, what are the tools they use to poke and prod at this foundational system? This is where we get into what they call the machinery of proof theory. It turns out they have a whole toolkit for this. They use things called natural deduction systems, which try to mimic how we humans actually reason step by step. They even set up dialogue games, where a proof is like figuring out the winning strategy in an argument. They also look at it from a computer science angle. But a really key area is what's called the implicational fragment, which is just a fancy way of saying they focus only on the if-then part of logic to see its purest structure. And when they're zoomed in on just those simple if-then statements, a proof can actually be visualized as a tree. Every step in the argument is like a new branch growing, and by studying the shape of these trees, how they grow, how they connect, logicians can spot these really deep hidden patterns in how proofs are built.
Okay, so we know it's simple, we know it's constructive, but how does this all relate to the logic most of us are used to, the kind we see in everyday math? Let's build a little family tree to see how everything connects.
Right at the very center, the absolute heart of our family tree, we have the smallest, most fundamental piece, minimal logic. This is our foundation.
Now let's build on top of that. Wrapping around that minimal core is the next layer, intuitionistic logic. It has everything minimal logic has, but it adds just one crucial new rule for how to deal with contradictions.
And finally, the big one, encompassing all of that, is classical logic. This is the system most of us learn in school, the one with rules like a statement is either true or it's false, no in between. So as you can see, minimal logic isn't some weird cousin. It's literally the shared core of all these more powerful systems.
So let's zoom in on that one key difference. Minimal logic gives you the absolute base rules for building an argument. Intuitionistic logic takes all of those and adds one more big one, a principle for what to do when you hit a contradiction. It's sometimes called ex falso quod libet, which basically means from a falsehood, anything follows. If you prove something is false, you can then claim anything is true. Minimal logic is so strict, it doesn't even allow that move.
Now this is where things get really, really cool. Because minimal logic is so simple, and it's at the core of these other systems, it can be used for something amazing. It can act like a universal target for translation.
This process is just awesome. You start with a big, complicated proof made in classical logic. Then you run it through a special algorithm that basically acts like a filter, stripping away all the extra rules and assumptions.
And what comes out the other side is the clean, simple core argument, translated into minimal logic. It's like taking a dense, complex novel and boiling it down to its essential plot points.
And believe me, this isn't just a neat party trick. This translation process is used to prove some major results, like Glivenko's theorem. This theorem builds a formal bridge between the classical and constructive ways of thinking, showing they're more deeply connected than you might think. And that's a huge deal. It gives mathematicians confidence that these two worlds aren't totally alien to each other.
So we've kind of established that minimal logic is weak, right? It has fewer rules, it can prove fewer things, but here's the twist, and it's the whole point of our discussion today. This apparent weakness is exactly where its true power comes from.
So why does any of this matter? Well, because it's so simple, it gives you this crystal clear space to analyze the tiniest nuts and bolts of a proof structure. It's the perfect, clean endpoint for those translations we were just talking about, a common language for all proofs. And by studying it, we get to see the shared DNA of all these stronger logics, which helps us get closer to answering the ultimate question, what makes a proof valid in the first place?
And that just leaves us with one final big question to chew on. We always think that adding more rules, more power is better. But if the simplest, most stripped-down logic is the one that actually reveals the most about the true structure of a proof, it really makes you wonder, doesn't it? What important details are all of our complex, powerful rules hiding from us?